Okay. Hello, everyone. Can you hear me well? Yeah? Okay. So, I'm Michał. Mm, I came today to speak about AsyncIO in production, war stories specifically. And these are indeed war stories because they happened in production. And production is basically war. So people are shouting, screaming, there are shots, everything's burning, and that's the life in production. So at Akamai, we are really specialized in being in production, and by specialized I mean we deal very well with the unexpected, mostly because we have the vastest network of servers around the world. So we have more than 250,000 servers. And you can imagine with that amount of servers, a lot of things can happen. We can have a disk failure, you can have network issues, so really a lot of things. So I would say that Akamai is great at dealing with incidents, with problems, with war in production. So I'd like to share my experience with some specific battles, and particularly our battles with AsyncIO. So we have a lot of servers, and we can do really cool things with them. So we can basically deliver static content to basically any point on the earth, and it'll probably be the faster delivery possible. We can protect our clients against web attacks, and we can, for example, stream data. So who watched Apple's keynote that was transmitted last month? Okay, so some of you. So the entire keynote was transmitted using the Akamai's network, and we haven't observed any incidents, any problems. So I hope that the quality was really good. So what I'm doing at Akamai is working on frameworks and tools. So before that, I had a small episode as a particle physicist as I worked at the LHCb experiment at CERN. I was working on implementing data quality monitoring system and partly some data quality analysis. Then I pursued PhD at AGH University, where I was working on a system to aid search and rescue operations by Gopher. After that, I worked in Printbox, which is a really great Python startup in Krakow. I know that the guys from the office are watching the talk, so yeah. And I'm particularly proud of one of the programs I wrote while at Printbox, which was designed to auto-scale and bid on the AWS EC2 spot market. And from what I've heard from my colleagues, the application has been running for 3 years now without any major issues. So that's something to be proud of. And now at Akamai, you can see that I'm working on more than Python stuff, mainly because my job is to be sure that we are using just the right tool for the job. So Python, in my opinion, is the most elegant, simple, and beautiful language that we currently have, but it's not suitable to solve all life's problems. So, don't let anyone tell you that AsyncIO or any other technology or methodology is a silver bullet, because Now I follow the AsyncIO world, and there's really a lot of presentations saying that basically follow the same pattern. So we had a service, it performed this many requests a second or a minute, then we added AsyncIO, and now we can have 3 times more network, the three times more traffic. So it doesn't work like that. AsyncIO is not a silver bullet when it comes to performance, but in some cases it's really well tailored to the problem. So it is indeed beneficial to use it, and I'm going to tell you what are these conditions projects. So first of all, let's see how what's the async actually, and let me just run a quick show of hands. Who has ever written any asynchronous code in any technology whatsoever? Okay, most of you. And who has written that code in AsyncIO? Okay, some of you. So let me just power through the introduction. So basically, the most simple way to execute your code is sequential or serial execution. So you have a simple job. For some reason, Go programmers don't like documentation. So on this example, a gopher is burning documentation. So its job is to simply move books from a pile and throw them into the fireplace. So we have one entry point, one output, and one worker. So this is serial execution. Then we can parallelize that. If our pile of books is big enough, what we can do is to divide it to several groups. We can add more workers, and we can try to execute everything in parallel. So with this execution, actually, more than one thing is happening at the same time. And then we have concurrent or async. So you can see that we have many workers. They are performing many tasks, but you have only a single entry point. So you have a single pile, and one gopher can be at that pile at the same time, and the same thing applies for the fireplace. So with that, we have one pipeline, a lot of tasks, because these gophers actually are doing different things. One is just moving stuff, one is taking from the pile, one is throwing books to the fireplace. So a lot of stuff, but at any given point in time, there's only a single thing happening, especially in let's say in our connection to the outside world, so our input and output. So this is how Python does that. We have this thing called IO loop. We have tasks. We put tasks into the IO loops. Tasks are usually wrappers for coroutines. So you can have a coroutine calling a coroutine. And then when its async job is done, we basically just the event loop knows that the task is done, and it can fetch the results. So a bit of history, because a lot of people is saying that AsyncIO is super young, we shouldn't use it, it's immature. So AsyncIO has been around, at least the idea of it has been around since 2012. That was the moment where when someone posted an idea to the Python Ideas mailing list, and it actually had a really funny title. So it drew the attention of Guido. Then Guido, in 3 months, formed PEP 3156, and roughly 18 months later, in March, there was a first release, 3.4, with the AsyncIO in it. So the API was released as a provisional API. That means provisional stands for you need to be mad to use it, especially in production, because it's subject to change, and because it's just like a demo of what we can do, how you can start thinking about it. And what I love about Akamai is that we have places in our software where we need to be rock stable, super reliable. We cannot have any downtime or problems whatsoever. And we also have places where we can experiment and try new things and approaches and see whether it would be beneficial for us. So we started using it. And back in 3.4, the basic syntax for AsyncIO was to use AsyncIO coroutine decorator and then yield from statement. So in 3.5, the next version, a lot of features were introduced. So there was async await keywords, there were asynchronous iteration, asynchronous context managers, and in 3.6 we've received asynchronous generators and asynchronous comprehensions. And since 3.6, the API has been declared to be stable and actually usable. Okay, so let's look how the AsyncIO code looks like. So this is a simple loop, the part in the top, a simple loop that queries the database for some data and runs some task in an asynchronous fashion. And who can tell me why this code is only halfway asynchronous? So the code is only halfway asynchronous because the await statement, and this is a common misconception with AsyncIO, await statement means wait for results. So if you write your code in AsyncIO and for each asynchronous call you have await statement, then you're basically running a synchronous code. So for that loop, you have for getting data from the database, you need to wait. And only after the data is sequentially for each of these queries is being delivered, then you can run the task asynchronously. So what you can do is to wrap these two coroutines together and run something like AsyncIO gather, which basically tells the interpreter to run all these tasks independently, and only after all of the results are back, then to continue processing. But sometimes you have something more difficult to do. The processing takes more time. So what you usually want in that situation is to use either a thread pool executor or a process pool executor to just asynchronously delegate your task to that executor. If it's a long-running task, then you probably want to have some timeout, so you don't wait on the results unconditionally. And also because you're running a pool of processes or threads, you don't want to be blocked forever if all the tasks are stuck. So for the more modern version of that code would use an async timeout module, which is an async context manager, just measuring how many times the coroutines inside that context can execute. Okay, why AsyncIO exists at all? Because what you can do in AsyncIO, you usually can do with threads. So we had concurrency before AsyncIO, and it was based on threads. So someone could say that it's just complicating the way we write code. So I would say yes and no. Because with AsyncIO and with asynchronous task coroutines, you can do much more in terms of how many things can you run at the same time. So before working on AsyncIO, I've spent a lot of time working on the parallel code. So I would say that for Python, I would be pretty scared to run more than 200 threads, and it's like it's a really high value. I would usually stop around 30, 50 threads, depending on the problem. Because with threads and with GIL, you know that they all fight to reach the interpreter. There's a lot of communication, synchronization, and a lot of CPU time is basically wasted to just manage the threads. So with AsyncIO, we've been successful in running thousands of asynchronous tasks at the same time, tens of thousands. So we can do much more in terms of this concurrent execution. What more, you know, because AsyncIO didn't invent asynchronicity in Python. So modules like Twisted or Tornado were doing it before, and they had a way to achieve that. But basically, because running things asynchronous requires, or at least the standard approach requires having an event loop, then everyone had to implement an event loop because CPython wasn't optimized for that. You actually, the performance could have been better. So, you know, a lot of code was duplicated just to prepare everything around the operating in an asynchronous manner. And also, like I mentioned, with the standard implementation of an event loop, there was an option to implement to modify CPython just to achieve better performance. Okay, so let me start with the first story. So one of the first project in AsyncIO I worked on had AsyncIO and threads in it. So basically, AsyncIO is running stuff out of order, and threads, using threads also means that you'll run things out of order. So we started with a bit of a headache. We were not super experienced, and an application that uses AsyncIO and threads is very, very difficult to maintain, operate, look for bugs, and fix them. So a lot of times we actually received these kind of errors, and I would say these are the greetings from AsyncIO to the newcomers. So what's important is that you need to fetch every single result, even if your function or method is not returning any result. You should still await it, just to be sure that there was not any exception in it. Unless, of course, you handle all the exceptions inside. Or maybe there was some error or some instruction that modified your flow, and you didn't await it an instruction because you had to go out of that scope. So in that case, the task is basically destroyed. It's garbage collected, and in case of these errors, you don't get these nice messages with stacks. You just get these things. We also run into what I would call dependencies nightmare. So let's assume that we have an application that is a Tornado application. We want to use AsyncIO. Currently, IO loop in Tornado is a wrapper for AsyncIO IO loop. So you want your database to be communicated with in an asynchronous manner. You have an async application. So there's a module for that, Momoko, which is an async wrapper for psycopg. We also wanted our application to be fast, so the standard IO loop is written in Python. It's not super performant. So there's a replacement called UV loop, which is a wrapper for libuv, which is a library in C, and it's an in-place replacement for the AsyncIO IO loop. So it just switches the loop itself. And then we wanted to run the application in production, so we had to have tests. So we used an async test module to get rid of some of this low-level stuff that you need to do for async tests. So if you look at the presentation now, these are the things that we run into. So basically, Tornado is okay. It's a very great module. However, Momoko is a pretty dead project, so it hasn't been contributed to, I think, either in a year or 2 years. So it's basically gone. UV loop, because it's a Tornado, and IO loop is a wrapper for AsyncIO IO loop. So if you add UV loop to it, which is another wrapper, then you end up with a few levels of wrappers just to achieve the performance you want. And actually, that might cause some unexpected results, because async test, as we've learned when we were implementing the application, is not compatible, or at least was not compatible with UV loop. So we had to run our tests with the standard AsyncIO loop. And actually, we learned at some point that one of the modules we were using relied heavily on the implementation of the AsyncIO loop. So we should never rely on implementation of internal mechanisms or private methods, etc. But in some modules, their developers do. So we actually learned in production that one of the modules is not compatible with IO loop, and we were not able to test it beforehand, because we had to switch to the standard loop because of that tests. Also, we started with Python 3.4. So we basically had AsyncIO coroutine decorator and yield from syntax. If we wanted to use, all the features of the new releases, we had to change all of that to async await syntax. And actually, it's even more complex, because Tornado had asynchronous execution before AsyncIO. So this was the official way in Tornado to write async code. So we had Tornado coroutine decorator and then yield, and not yield from, because yield from was added in I think 3.3, and Tornado was created way before that. So in some projects where we had Tornado, we had to use yield. In other projects where we didn't have it, we had to use yield from. So basically, a nightmare. Okay. So we've learned our lesson, and we decided that we'll use AsyncIO only for really small and simple services, basically microservices. So we had a task, a project to implement an asynchronous HTTP client. So this is like the core functionality of the client. So we are opening a TCP connection, then we create HTTP client, we send a GET request to some server, which would basically open a streaming connection. And of course, if you want to iterate, there's no aiter function. You need to use the dunder method. Then we had certain timeouts, and then we iterate over the content with dunder method again, because there's no anext function, or at least there was no anext function in that release. So this was quite unusual, and we learned that a bit later, because basically the application was opening a lot of these connections and were fetching data from these streams for hours or even days. So that's unusual for HTTP, and this is what we observed. This is our memory usage for that service, and you can see just by looking at it that it clearly indicates memory leaks. So we contacted the modules developer, and basically he said that it would be so much work for the project, and this case is so unusual that he won't fix it. So yeah, that's why I'm not saying what module it is, but if you know async HTTP modules, you can probably guess. Yeah, so in this particular case, we couldn't find a working AsyncIO HTTP client for that application. So for long-living streaming HTTP connections, we had to use threads, basically. Okay, another story, and this bomb is an indication of what it's going to be about. It's a story of an Elasticsearch indexing client. So who here has worked with Elasticsearch? A lot of you. Great. So in my opinion, Elasticsearch is a great storage, is a great database, and we use it happily in a lot of places at Akamai. However, it has its quirks, and it's really performant, but it can also behave very, very odd. So this Elasticsearch pushing client was indexing some data into Elasticsearch, and we observed that for some reasons, sometimes the application just blow up. So like memory usage goes through the roof, and the application is gone. And we were interested in what's going on with it. So basically, Elasticsearch, if you have like a constant traffic, you are pushing to the Elasticsearch at a certain pace, then everything is okay. But if you're starting having spikes, then the Elasticsearch can behave very weirdly. Apart from it giving like I think it's 429 response saying that too many requests were made. It can like stop processing for a second to deal with garbage, or it can suddenly for a few seconds process very, very, very slowly. So we also observed something similar. So I'm reusing the picture, but it was basically we saw even more rapid growth. But with that memory growing, we also saw CPU growing. So what actually happened was that we received data at a constant speed, and if there was a spike, Elasticsearch took longer to process the data. And actually, because we weren't limiting creating these async tasks in any way, then we might have ended up with, let's say, 1 million asynchronous tasks that would basically be pushes to Elasticsearch. So we've also learned that the more tasks you have, the slower your async application will work. So we had to find some way to limit how many tasks can we run at the same time. So we found a really interesting module called AIO jobs, which basically implements two queues, active queue and pending queue. So you can limit how many tasks are in the active queue so that your memory won't blow up, and at the same time you can have a pending queue so that you can basically, if everything is okay, it's just a buffer for those spikes. And if we have too much data, it's better to just drop some data and time out than to crash the entire application. Okay, so up till now, I've been, I think, quite pessimistic. So let me tell you that in some project, AsyncIO worked great for us. Okay, so a few months ago, we developed this really tiny microservice that had only one simple responsibility, and its responsibility was to make DNS queries. So we were getting data in batches, and it took, for our preliminary implementation, it took 12 hours to make DNS queries for any given batch. And we thought that, and we of course fine-tuned the numbers of threads to find the best possible amount. So we prepared a proof of concept of how the code would look in AsyncIO. And actually, because UDP is a super light protocol and DNS is implemented over UDP, we received, with basically this one simple line, we received a reduction in time from 12 hours to 8 minutes. So with UV loop in place and with just a standard AsyncIO DNS implementation, or maybe that was the one from the AIO package. Nevertheless, there's a huge difference, and with just a single interaction point with AsyncIO, the speed up is really impressive. So another story, and it's a really recent and fresh story, is about the services that communicate only with messages. So our job for the last few months has been to implement some application which has an HTTP entry point and an HTTP output, but in the middle it was supposed to have a few services that would basically analyze some data, push it to one place, push it to some other place, fetch some data. And we thought, like, these are microservices. We want them to be microservices. We don't want them to be REST applications. So we will use message brokers in AMQP protocol in particular, so that the communication between these services will be done only over AMQP. So because AMQP is asynchronous in its nature, and because there are actually quite good client libraries written in Python for AMQP message brokers, we've achieved not only very beautiful design, but also the code is very simple, is maintainable. So with using AMQP, we haven't had like a single problem related to the communication or the AsyncIO itself. So if you're using AMQP, I would strongly advise for AsyncIO. So what are pros and cons of using AsyncIO, in my opinion? Well, you can have a performance boost if your application is relying on I/O. So if your application is doing a lot of processing, AsyncIO, it's not magic. It doesn't like magically boost your application. You can do more stuff instead of waiting and communication and synchronization comparing to threads. So it's great for that. And basically there's this asterisk next to DB, because with most DB we communicate using sockets, so that's network. So it's the same thing. When it comes to some, let's say, soft advantages, you receive basically a new tool which you could solve new and old problems which you've had. So it makes you think how to solve it differently, more efficiently, and it actually makes you follow Python progress and contribute, because until I started using AsyncIO, I've never hit any bug in Python in the Python interpreter. So if there was like a single new feature from a release to release, I was happy that yeah, that there's one new thing, so I will start using the new version. With that, with AsyncIO, it actually makes you follow and wait for new releases because you want new and missing feature. What are the cons? Well, these missing features are the cons. There's also a lot of known issues, which unfortunately are either small bugs which can be fixed quite fast, or they are architectural problems, like the problem with async iterators, which have messy and indeterministic cleanups. So from what I've heard, there's no plan to fix that until 4.0 because it's architectural. And there probably be some experimental mechanism in 3.9, but that's two releases ahead. Also, iter tools, the module I really enjoy using, doesn't have async support. So basically, we have async comprehensions, async data structure almost, and you cannot use iter tools with it. And also, what's really bad is that if you have like an external services like Zookeeper, Elasticsearch, if you use an ORM in the project, there are either very experimental and preliminary implementation, or there's a complete lack of the appropriate modules. So even if the modules exist, they are still young, many bugs and incompatibilities with each other. And actually, what's even a bigger problem is that our community is getting more and more divided, because some maintainers clearly state that AsyncIO is too complex, that they don't want to take part in it, and some of the modules are either really slowly adopting AsyncIO, or in some cases the maintainers said that they won't support AsyncIO. So, for example, have you heard about Curio project? It's developed by David Beasley, who's quite known in our community. So he thought that AsyncIO is really complex internally, and he created like a really simple implementation of it, just to start a discussion of how these things should be handled. And basically, a lot of people turned back from him, and they stood for AsyncIO, and now we have this separate project which deals with the same problem as AsyncIO. Okay, so what projects are best suited for AsyncIO? In my opinion, microservices. Like I'm not a huge evangelist for microservices, because they are just yet another tool to solve some problems, but they introduced some other ones. So if you have real microservices that are small and they do one thing but good, then AsyncIO is great for them, because if the main flow, the business flow, is not very complicated, if you introduce AsyncIO to it, it's more complex but still maintainable. Project with a small list of dependencies, mainly because you have a lot of incompatibilities with a lot of modules, mainly because a lot of the modules written before AsyncIO, they used threads for communication, and it's not very safe to use threads and AsyncIO, as I mentioned before. So simple HTTP APIs, the modules doing that are actually quite reliable right now. Projects with big load, big traffic, but light processing. So if you have a lot of requests, but these requests translate to small tasks internally, so they are handling each request takes milliseconds and not seconds or more, then AsyncIO is great for that. Projects where threads are not enough, so if you have like many connections to handle like thousands of them, or you just spend a lot of your time on threads doing I/O, network I/O, then AsyncIO should be a fine replacement. And also projects where the rest of your technology stack is well understood, so that if you introduce AsyncIO to your stack, you can at least imagine or expect how will it interact, and you can expect the unexpected. Okay, and what projects are not suited for AsyncIO, in my opinion? Projects that heavily rely on threads or processes which are not doing network I/O, or if the modules, if their dependencies heavily rely on threads. Like for example, in the first project I mentioned, we had threads responsible for communicating with the Zookeeper, and the most mainstream module for that in Python is Kazoo. And what they say is that the module is not only not compatible with AsyncIO, but they don't have any plans to rewrite it or to make it compatible. And we thought that, okay, they said this, but we don't see how these threads cannot exist in their own space. So let's use it. And we've experienced quite a lot of issues with communicating with Zookeeper and doing our own AsyncIO communication, and the same actually with AMQP. Also, projects where processing of a single task takes a lot of time. So minutes, hours. That's not a good idea to have AsyncIO working on that. And projects doing uncommon stuff, because the modules are quite young. The developers don't expect you to do the uncommon thing. So in our case, it was long-living HTTP connection, but in your cases, it might be something different. So if you're doing something uncommon, then you need to be very, very cautious when using AsyncIO. Okay, thank you very much. That's everything I have. And if you have any war stories on your own and you don't want to ask questions or talk publicly, then I strongly encourage you to approach me and to have a chat. Okay, thank you very much. I'm relieved. It's the worst kind of thing when you give a speech and there's no questions.
Okay, so I was wondering if you evaluated G event at the Akamai, because I think that while it solves the problems in some similar way, the way it monkey patches solves some of the contrasts that you outlined in your lists. Like, for example, requests or other services that would normally work in a synchronous mode. Yeah. And also, if you evaluated it, do you have benchmarks against AsyncIO?
Okay, so I'll start from the second half of your question. So on the internet, because it's a buzzword right now, AsyncIO, there's all sort of benchmarks. Even if you go to, I think, Curio or UV Loop, you'll have like all the horizon of possible solutions. So I'm not sure right now whether G-Event is faster than AsyncIO. However, at Akamai, at least in my team, we haven't used G-Event. I used it in one of my previous projects, and actually got some problems with it, mainly because, like you mentioned, it monkey patches some functions, modules, and in these cases, in these rare but very painful cases where a module developer relies on a specific behavior of the standard implementation, then bad things happen. And actually, I think we were using it with some version of Django, and we had problems with it. Yeah. Okay. Oh, is the mic on?
Now it is. Right. So, are there any debug utilities for AsyncIO?
So I think the standard debugger is capable of debugging AsyncIO. I know that I personally use IntelliJ or PyCharm, and I don't think there's any official support. So mostly when something goes wrong, you have your standard tools like thread dumps and and memory dumps, but also because AsyncIO has, or at least its event loop has a debug mode, which is very, very verbose. So you can actually get a very detailed log of what's going on under the hood. But in my opinion, I think we should be able to set some debug levels on it, because basically right now it's on or off flag, and for the default setup, it's just so verbose that it's really difficult to understand what's going on, especially because if you create a task, an asynchronous task, let's say it's a communication task with the DB, actually internally it won't be just a single task, but it will be a group of tasks. So they will be put into the event loop, and they will execute in some order. They will wait for each other, but you will get all the information about every single internal task, which you might not even recognize what it's doing there, because it's not your code, right? So I'm not familiar with any mainstream debugging tools that would help with AsyncIO.
Okay, thank you very much. Okay, another question. Do you have an experience with like testing, let's say, multiple simultaneous invocations of a method, like a unit test, but for, let's say, 1,000 at a time, to see if they like break each other or something?
No, but do you mean like you have a coroutine and you invoke it 1,000 times?
Yeah, I'm just wondering if there is like a difference in behavior. Like if I unit test it just one at a time, and like do I also have to check it if it's like 1,000 or something, or like will it behave the same?
Well, if the CPython implementation is correct and valid, then you should get the same result every single time. Actually, Raymond Hettinger has a very interesting method of testing async code. So, because when you are testing async code, async was created for coping with network connections, and network I/O. And usually in tests you don't want that, right? And especially in unit tests. So you either mock or or you have these really smart VCRs where you can record contents and responses and use them to test without any real network. So his idea is to put random sleeps in your code, so it runs when it's tested. And actually, he proposed to just put it not in the test itself, but in the implementation. So in the actual production implementation. So, but to switch it with some debug flag. So I would say that if you don't use an actual network, you can actually introduce some latency or some problems, like partition or spikes and slowdowns. But it's controversial. I wouldn't put sleeps into my production code and forgot to turn it off. It might happen.
Yeah, it's a bad idea. Thank you.
Yeah, thank you.
Any more questions?
Have you ever had any problem with scheduling tasks, some starvations of them in production?
Yeah, basically, if you let's say for the project where we had this long-living HTTP connection, so like if your task is fetch data from the stream, and let's say that the streamer itself is very strict about heartbeats or getting some pings from the client to fetch data, etc. So if you are stuck doing other things, and because it's asynchronous, you cannot, make sure that I want to run this and I want to run this before that, right? So yeah, in case of for a really big traffic, if for some reason some stream is more privileged by the scheduler, by the event loop, then we saw cases when we had starvation for some other streams before let's say we weren't fetching data for 60 seconds or more, and then we got disconnected from the streamer. So yeah, that's and actually it's a really, I would say it's a really big problem, but it's the same with threads, right? If you have pre-fork architecture, you create a fork for every connection, then also you cannot make sure that one thread won't be starved because others will get to the resources and that one don't. So yeah, I would say that that scheduler, which I mentioned, makes sure that AO jobs scheduler makes sure that your memory won't blow up. But for now, I have no idea how to protect tasks against starvation.
Okay, thank you for the answer.
If you have more questions, please reach me how
Yes.
online or maybe
Or
on
right
after
now.
party.
Yeah.
During after party, great. Thank you,
Thank you very
Michał, for
much.
your presentation.